Welcome to the AIA Building Science webinar. Today we have the pleasure of having Elliot Benner joining us and present Narrowing the Gap Between Design and Performance. Elliot's facades and energy are Elliot's passion. He has an electric background spanning 30 years, from manufacturing insulating glass unit to testing building envelopes. He has worn many hats, including his journey in the construction industry, repairing windows and moving on to glass fabrication, consulting, and testing. He has the privilege of working with Israel Berger as a senior consultant and with the pioneers of unitized curtain wall business, so it's like Werner Kalo and Ladislav Holford. Elliot is a voting member of ASTM Committee DO1, EO5, E6, and E36, and the member of American Architectural Manufacturers Association. Elliot is also a member of the New York City Department of Buildings Advisory Committee for Chapter 17. Just in case you're wondering what chapter that is, that's Special Inspections and Testing. And the NYC Facade Inspection Safety Program and the NYC Energy Conservation Code. Just a quick thing, if you guys have any question, there's a button in the middle for questions. So just type in any questions that you have and we'll get to that at the end. And at the end of the program itself, the AIA credits will be showing up. So if you forgot to sign up or anything, they'll be there. And with that, Elliot, you can start.
Hi, good afternoon, everyone. Thank you, Satpal. Thank you so much for the introduction. One quick warning, I'm actually doing this from a farm, so you may hear some roosters in the background. That's the chicken warning. So just in case, forgive the disruptions. Let me see. Is my share screen coming through?
Yeah, we see your share screen.
Okay. I don't know why I'm not advancing. Okay. So this is the title, Closing the Gap on Local Law 97, Getting from How to Why. We've been talking for years about why we need to have a carbon reduction policy in place and a meaningful way of getting there. But it's really time for us to now start figuring out how we do that. This is the AIA Quality Assurance. This program is registered. Questions related to specific material and services will be addressed at the conclusion of this presentation. If you guys can just put the questions in the Q&A, hit that Q&A button at the bottom, you can put the questions in there for Satpal to read later. So the learning objectives are familiarizing yourself with current and emerging standards for building enclosure testing and how it relates to commissioning and retro-commissioning. Retro-commissioning is going to be critical for achieving compliance with Local Law 97, which is very different than achieving compliance with the building code and the energy code today. And as architects and engineers, most people have been trained and have practiced how to meet the code and sometimes how to surpass the code, which we usually want to do as professionals. But this is going to become more and more important because there is a difference between prescriptive and performance when it comes to energy, facades, mechanical systems. The second objective is why prescriptive design standards are not viable and why we need to go above the normal way that we did things. Third is evaluating your role in preparing a building for enclosure testing and really for retro commissioning. I'm not going to talk that much about testing. I'm going to talk about the teams that need to be developed to perform commissioning and retro commissioning, and why, as designers, engineers, consultants, you guys have critical roles in that. But there are other participants that need to be involved and informed. And then recognize the building enclosure testing process. And we'll go through it one by one. So first, what is Local Law 97? So Local Law 97 was developed by politicians, not engineers and architects. And it was developed to limit carbon reduction by measuring energy bills. So there are no metrics that we normally use, R values, U values. There's no prescribed method of getting to local law 97. It's simply a measurement of how much energy is being purchased at a specific building, at a specific address. It's all the energy going into that building. It's not just the operating energy for the building, like lighting, heating, water pumping. It's all the energy going into that building. The limits are established based on the size and use of the buildings. So covered buildings or any commercial building that's 25,000 square feet and over is part of Local Law 97. Local Law 97 applies to those buildings. And the bad news is complying with the energy code, passive house, net zero, while all these programs are great, complying with those programs or with the code doesn't ensure that the building is going to meet the Local Law 97 compliance requirements. And Satpal mentioned that I was on the Energy Code Revision Committee the last cycle, and we worked for 3 years, and then the mayor got on the phone or got on the news one day, April 18th, 2019, and announced that we weren't going to build any more glass and steel towers in New York City. And that kind of put a damper on all the work we had just done because they basically overrode the energy code. So what is retrocommissioning? Retrocommissioning is a practice of establishing the functional performance of an existing building. So that means, how is the building functioning? How are the major systems of the building functioning? And how do you measure the performance of those major systems? You start with the basics. The building information statistics. What type of building is it? How many occupants are in it? When are the occupants in the building? The footprint of the building, the height, the wall types, the roof. Is it a mixed use building? Is it residential, commercial? What kind of mechanical systems are in there? Is it a residential building with P-tax? Is it a commercial building with 4 huge mechanical systems? That's all. Okay, there's the first comment. And this is important work. And this is important work that can be done by the owner for the most part, because they do know a lot of this information already. So they are an important and critical part of the team. It's not just the engineering and architecture side that is establishing these factors. Operational, what are the approximate occupancy rates? Do it by hour, seasonally. There are times of the year when a building is higher occupancy, lower occupancy, times of the day. Most buildings, commercial buildings, already have controls at entrances. So you swipe your card to go through a turnstile, you sign in. All that data exists and is really good and easy, pretty easy to mine. So we want to talk to the owners when we start the process about how they can get this information collected. It is a team sport. There's going to be a program manager, an architect, a mechanical engineer, a facade consultant, and an energy efficiency consultant, and then the building management system specialist. You guys are probably hearing the word BMS more and more often. Some of you may already be installing them, servicing them, working with the information from them. The program manager is the person who ties this all together. Lots of times it is one of the other people. It could be the architect that works with a building already and is approached by the building to say, hey, we don't have a Local Law 97 compliance plan. Can you help us get to a point where we have a long-term plan? Because it is a long-term plan. It's not just about changing windows and putting new pumps in for the water pumping system. It is a master plan that needs to be done. So any one of these people can also be the program manager, or the program manager can be someone completely separate, say in the management company of the building. We're going to talk more about the building management system. It's very important. So measurements, and how do we measure things? In the old days, my job was very simple. I sprayed water on windows. I measured the air leakage through windows, and it was more or less easy. We had to hit a certain number and that was it. Today, we really need to figure out what the existing envelope of the building is doing, where the mechanical system is not functioning correctly by balancing, testing and balancing. Um, we've been using a lot of the wrong metrics. Uh, One of them that we harp on a lot is called U factor, or most people refer to it as a U value of a window system. That is the measurement of how much energy flows through something. U value is also referred to as transmittance. And what's transmitting is heat. So, how much heat can flow through a body, an aluminum window frame, a piece of plywood, a piece of sheetrock, brick. Every one of these materials, concrete, has a U value, a transmittance value, or an emissivity value. And it's the value, it's the physical property of that material to allow heat to flow with it. That's what U value is. U factor is a rating system that the fenestration industry developed to be able to say this window is better than that window, and a third window is even better than that one. It was the only way that we could introduce this and codify window efficiency, because the science behind it, when we started putting this in 20 years ago, started putting in the code, the science behind it was much more complicated than most people were accustomed to and capable of working with. So a rating system made sense, just like tons of other things in the code. The energy code and the building code are based on good, better, best. And this is also one of the things. The problem with that is it's fine for saying this window meets the code, but when you want to know the window's effect on the energy loss in a building, you really need to get deeper than just a rating, an ABC. You need to actually have a number. And that's one of the problems that we have with the current way that we perform energy evaluations of buildings. So I like to tell people you need to fall in love with a model. And while that may not be your ideal model right there, modeling is very, very important. And we have to start with basics of the building. Some people are probably already using Energy Plus or eQuest or one of those, what we call a DOE2 based energy modeling software package. It's all based on an old an old engine that was developed by the Department of Energy, again, 25, 30 years ago, when computers were the size of your living room to run the software. And it was very, very simplified and not that robust. Today, your iPhone is probably more powerful than the computers that were used to do the original DOE2 software. So we've come a long way, and we need to look at some of the more updated modeling packages that are out there, most of them coming from Europe, but not all. Um, we we like to refer to all of the high efficiency programs, and people talk about LEED and everything else. And this is not a knock at any of these programs, but I tell people try to find 3-year post occupancy studies to see how LEED, silver, gold, and platinum buildings are doing actual energy use compared to modeled energy use. And it's not just LEED, but any of the programs and even just code compliant buildings. When you do comp check, you are getting a number that is supposed to represent the energy use of the building. We're really short, or it's very, very hard to find any actual data that has tracked post occupancy energy usage past the first year. And the reason is that we think as architects and engineers and professionals that if we put it on paper, it's going to get built the way we intended it to be built. And that doesn't happen in the real world. And that's the gap. That's the gap that we have to try to close with commissioning and retro commissioning. And I'm hoping that we develop the tools over the next few years to do that. So what do we do? Do we throw the model out the window? No. We work with what we have and we do a global model, which becomes a tool for decisions. So we work with eQuest or Trace or any of the software that you guys may already be working with, but we don't use it as a decision-making tool. We use it more as a guidance-based tool. So we want to look at the overall building numbers as a comparative tool. We want to compare what we do, any upgrades we make, and see how that's affecting the overall number. Because buildings, especially buildings in New York City and Boston, Philly, very, very complex. You know, they're tremendous organisms that is very, very hard to put into a spreadsheet and figure out how efficient they are. Um, I tell people start simple. We don't need to be complicated. Start with energy bills because that's what we're going to finish with when it comes to local law 97. How much energy is the building purchasing? And that can go into a simple spreadsheet. And you want to look at that and look at it for the past 5 years. Look at it seasonally, look at it monthly, compare it to occupancy, compare it to the weather data that is available, but honestly, it's a pain in the ass to get sometimes. But we want to do at least 5 years of historical weather data because the 5 year data will level out one bad winter or one extremely warm summer. It will average it out. So you'll be able to look at things and say, okay, here's the average energy use by month or by season or by week. And this is what's happening. And then start charting that against occupancy. And especially in commercial buildings, that's really, really important. In residential buildings, occupancy trends are pretty, other than COVID, which unfortunately screws up our recent data, but occupancy in residential buildings tends to follow a pretty steady pattern. People are home at night, they're not home during the day for the most part. So the majority of your energy usage is happening when people are in the building, although some buildings are still very wasteful when there's low occupancy. Business operations, occupancy levels, all those things need to be tracked. And honestly, this needs to be done by the owner or the manager of that building. They should be collecting this data, and the program manager needs to explain to them why that data is important. Because I can measure the efficiency of a wall, but it's no good to you unless you have other data to compare the energy loss to. So if you have a floor, 20,000 square foot floor plate in a commercial building that's using, I don't know, 5 kilowatts per hour of energy, and that's when it's during COVID, and now it quadruples because there are people filling up that office space. That's an important thing to factor in, and that's important information to have. Uh, Loads, let me just go to the next slide. So loads, it's all about loads. All the energy that we can do something about is because we are heating spaces and cooling spaces. Those are the primary energy use things that happen in a building. So you're either heating a space or you're cooling it to condition that space. And how much energy it takes to do that is dependent on occupancy rates. A human body gives us 150 watts. A laptop computer gives off 180. This is in waste heat now, not the energy used to do functions on a computer. This is the waste heat that comes out of the fan in the back. Refrigerators, coffee machines, appliances, monitors, lighting, they all give off heat. And in high-rise buildings like we have in New York City, there's usually more heat, even in the winter, than we need to condition that building. So cooling is the dominant condition or the dominant function of an HVAC system in most high-rise buildings. Most residential buildings have lots of glass in them, or most that were built in the last 25, 30 years have very high percentages of vision glass. Vision glass lets solar gain in. It's higher in thermal transmittance. These windows become leaky over time. So we are a dominant cooling area when it comes to buildings over 200 feet tall. And we need to control that. That's where we're using the majority of heat is in heat of energy is in heating and cooling. I don't know how many people have done a blower door test on one of their projects. It's an ASTM E779 test. That's a test for air leakage. Why are we required to do this in buildings that meet the 2016 and 2020 energy code? Because air leakage is one of the major factors for energy loss. People don't realize how much their buildings leak air. And when they get taller, it gets even more compounded due to the stack effect. So the taller a building is, generally the more it's going to leak. Even if the facade is a good facade, there's always leaks in the building, loading docks, service doors, entrances that don't have properly designed vestibules. These are all sources of air leakage, and they can be substantial. And when cold air gets into a warm building and warms up, the heat rises and it creates suction that pulls more and more air in from those leaks. And it shows up as front doors that are hard to open and close, whistling in elevator lobbies, elevators that make tremendous amounts of noise when they go up and down, elevators that have problems with the doors opening and closing. These are all very, very common problems that we see in high-rise buildings that have excessive air leakage. Lighting is another important factor. It was the low-hanging fruit for the last 10 years. There were many programs out there for people to upgrade to LED lighting, and I think a lot of people took advantage of it, and that's a good thing. Now we have to start hitting the hard things like the envelope. So what's in a name? The skin, the envelope, enclosure, the facade, these all mean the same thing. It's the six sides of the building, from the foundation to the roof. That's the building envelope. I'm in the building envelope business. I've been my whole life, as Paul said. No matter what you call it, that is the skin of the building. And the skin of the building has certain functions. It has to be the separation between the inside and the outside. It has to support whatever cladding is on it, so there's a structural element. It has to control air leakage, water leakage, and thermal transmittance. And hopefully, it will also control some of the solar heat gain that comes in through clear glass. I like to say that I'm in the measurement and verification business, not the testing business. We don't pass or fail people. We try to just perform a test correctly. And measurement and verification are two very important parts of that. So when we measure something, we're trying to determine a physical property or a physical condition of something. And that leads us to verifying new construction projects to tell the owner whether or not they got what they paid for, or whether that upgrade, whether you change those windows and actually did get the U value, the air leakage, all the things that we can measure, whether you got what you paid for and whether you got what you were promised. And that's going to become more and more important because as professionals, you're responsible when you sign on for a job to make sure that you delivered the project or that the project was delivered correctly. So measurement and verification are becoming much more important every year. Commissioning is the buzzword. I'd like to talk about it briefly when it comes to new buildings. So commissioning an envelope involves all different parts of the building. These are just some of them, and it involves now one big test at the end called a blower door test or a whole building air leakage test. The roof, the windows, air barrier, eaves, stucco, brick, rain screen systems, they all have subcategories of testing and measurement that have to be performed per the building code and the energy code, but also just to ensure that what you put on those drawings and in that specification are actually going to be what's delivered at the end of the project. Again, that is the gap. You can design it perfectly, and the GC can make a substitution of a material and unknowingly change the whole structure or the whole performance of a facade or a mechanical system or any other part of the building that's detrimental. And now all of a sudden that energy model, the comp check, they don't work anymore, right? Because substitutions are dangerous in 2024, extremely dangerous. When you design a building and you consult with a manufacturer who helps you detail something, and their product is the product that's going to work for that condition, GC doesn't know this usually. And they'll go and buy whatever's at the supply house or whatever's a little cheaper. And it all looks the same to them. And it's not. And we see this over and over again where one small substitution really affects the overall performance of the building. Air leakage, again, I'll go back to air leakage. It's one of the hardest ones to fix after the building is complete. Today, most people have seen blue skin installed on buildings, and for the last 4 or 5 years, the fluid applied membranes are installed on the surface of the exterior wall, on the sheathing or on the block. Once that's covered up by whatever cladding there is, terracotta, metal panel, brick, getting back in there and trying to fix those air leaks, which become water leaks, is so costly. No one wants to do it until it's a legal problem. This may seem overwhelming. It's really not. It's just getting back to the basics that we always did for many, many years, which is just look at every condition you have on the job. You have a foundation, you have below grade walls, above grade walls, openings, and a roof. Look at how they interact with each other. Look at the transitions between one system and another, and try to make sure that the owner understands that when they're buying TR1 and TR8 inspections or maybe commissioning, it's important to not just check off a box and say it's fine, or I saw the air barrier, so we're covered. No, air barrier continuity, which is what the code requires. Not that you see the air barrier on the wall. We like to refer to it as air barrier with a small a and B and air barrier with a big A and B. Air barrier with a capital A and B is the product. It's that blue skin, it's the fluid applied silicone that they put on. Air barrier with a small a and a small b is the skin of the building. It's the caulk, it's the roof membrane, it's the air barrier, it's the below grade system. It's the windows and doors. It's how all those things tie to each other and create one continuous barrier around the building that controls air leakage. Holes in that system wind up not only costing money, but most of the time turn into water leaks. So we need to do it to achieve the energy goals that we set forth in the drawings, but we also need to do it and make sure it's done correctly so that we avoid problems with leaks in these buildings. So again, these are the major components that you're looking at when you're inspecting during a normal commissioning project: fenestration, roof, air and water barrier, and cladding. If anyone needs help on what types of testing and inspection to do on this, I do have some stuff I can send out and help people with. It's important, as I said, most owners today are just looking at the sign-offs for the inspections and the commissioning as a sign-off, as a document that I file so that I can get my C of O. And it's really not. Every one of these systems is critical, and it's important that they are done correctly. So this is an example. A friend of mine from Portland runs a lab out on the West Coast, does lots and lots of blower door testing because the state of Washington and Oregon strictly enforce the practice of blower door testing on every building, whether it's a 40-story building or a single family home. Every building in those states gets a blower door test. It's called a blower door because you're taking one or more of these fans that you see in the picture and putting it into a doorway in the building. In this case, it was a service door and a loading dock. that fan either exhausts air out of the building or pumps air into the building. And the fan actually has measurement instrumentation built into it to see how much air is flowing through that fan. And if all the interior doors are open and all the exterior window doors are closed and locked, any air that's going through those fans is actually building air leakage. And we measure that air leakage in cubic feet per minute. I tell people, think of a balloon as a cubic foot, a party balloon, as being 1 cubic foot. So every cubic foot of air is one party balloon being introduced to that room. The room you're sitting in right now, just imagine how many balloons it would take to fill that room from floor to ceiling. We're saying 50 CFM of leakage is 50 of those balloons coming into that room from outside, which is unconditioned air, coming into the building. Every one of those balloons represents a cubic foot of air that needs to be reconditioned. So if the room you're in can hold 400 balloons and it leaks 50 balloons per minute or even 50 per hour, that means in 4 hours, that room is going to get reconditioned every 4 hours. And that's very, very costly to the environment, to the person who owns and runs that building, and to everyone that's sitting in that building, because it's not comfortable to have unconditioned air constantly exchanged through the envelope of that building. Okay, this slide's a little screwed up, but this is a difficult test to perform, which you could see from this picture. People in New York are not used to doing the test. They don't understand the process or how performing this test has to be scheduled into construction. These are a few pictures of our guys performing the test. In the bottom right-hand corner, you can see them sealing up a mushroom on the roof. I think the one in the middle was a job we did at West Point. Yes, that's a clinic at West Point. And this is a typical smaller building setup, a couple of fans in a doorway, and the guys are performing the measurement as we go. So now for something completely different. We need people to become experts at retrocommissioning. The reason is for every building that's being built right now, there's 200 to 250 existing buildings. And I think everyone's heard that there's many, many more existing buildings than buildings being constructed, which makes sense. As soon as we build it, it's existing. The problem is that we're dealing with old building stock, newer building stock that may not have been built as well as the older building stock. How do we tackle the job of making those buildings more efficient? It's very hard. From what I've seen out there, most people are looking at window replacement, some more modern air conditioning systems like heat pumps, and they're all a part of it, but they're not the whole thing. And we really need to become experts at it. So retrocommissioning, as I said, as soon as a building becomes built, it's an existing building. And the difference between commissioning, which is done during the course of construction, and at the completion of the building, where all the systems are actually commissioned, that's a more common thing that people do at this point. Retrocommissioning has to become part of our training and lexicon. Again, back to time and loads. We have to control those loads, and we have to understand the time that those loads are highest in a building. This is one standard calendar year. 8,760 hours that's the number we work with mostly. Why is it important? Because we have to start looking at things, drilling down to what happens during an hourly event. A lot of you are probably more familiar with heating degree days and cooling degree days. Those terms and those numbers were developed 60 years ago when computer power didn't allow you to model energy use by the hour or the minute. So we made this, again, averaged number called a heating degree day. And I'm not a fan, obviously. We do have the computer power today to use hourly weather data, use hourly monitoring at buildings for retro commissioning, and see what's going on hour by hour and measure it against the effects of weather, again, the effects of occupancy, and see how those are affecting energy usage. And that's very, very important. So how do we begin with retrocommissioning? Identify the main building envelope systems. How many wall types are on the building? Is there stucco in the back, brick in the front? How many roofs do you have? What type of roof? How old are they? How much insulation do they have? Same thing with the mechanical system. Develop a reverse model of the building. We want everyone to use local weather data that is available from NOAA, but NOAA is a little harder to work with. We're actually working with owners of buildings throughout Manhattan to try to access their building modeling system weather data. So a BMS system is the system that monitors and usually runs the mechanical systems. And most larger buildings have a weather station up on the roof. And we're trying to work with owners from the Freedom Tower up to the Bronx to say, we will give you discounts on the services we do if you'll share that monthly weather data with us that we need to start developing more localized models of the weather, because most people realize the weather on West End Avenue is going to be way different than the weather is going to be on 59th Street and Park. And that's because Manhattan's got tons of microclimates, as most of the boroughs do. Coney Island's not going to have the same weather as Court Street, right? If you're in Brooklyn. So we're trying to get that done right now. But there is enough weather data coming out of the NOAA weather stations at the airports at Central Park that's useful. In the future, we'd like to get it more localized, but for now, we're using those weather station data. Plug in the actual numbers. And ASHRAE level 2, which is what's referenced in the building code and by most of these programs and for building retro commissioning, it's not enough. I'm going to tell you right now, it's very, very mechanical system centric. It tells you to do an evaluation of the building envelope. It really doesn't tell you how, other than making a determination of whether the windows are dual glazed, single glazed. It's very basic stuff. You need to drill down more than that. Then we can create a dynamic model with this that can help us understand how the building is performing. So I'm going to go through the slides a little quicker now because we're getting tighter on time. Everything I need to know I learned in high school: conduction, convection, and radiation. These are the three main vectors of energy loss through an envelope. Conduction is body to body or body to air to body transfer of heat. Convection is the heat created by the flow of air, and radiation obviously is radiation like from the sun. Not to be confused with a radiator. Radiators do radiate heat, but they're really transferring heat in more ways than just radiation. So that's a building that was actually LEED Platinum certified. And we were called in 6 months after the building was occupied because the doormen and the people who worked in the lobby had to wear parkas all winter long inside the building. That smoke that you saw coming in through those cracks, this was at normal conditions. Smoke was getting in through this very beautiful looking lobby wall that ran from the inside to the outside. And unfortunately, everyone missed the separation line between the inside and the outside for the air leakage. This was one of the problems at this building, but it was a major one. Remember what I said before about stack effect? This is a 65-story building. That cold air comes in, it forces warm air to rise, it gets reheated, it gets heated rather, and this cycle just keeps feeding itself and feeding itself. More cold air comes in as the hot air rises. It leaks through penetrations in the top part of the building, and it just created an effect where literally every 3 weeks the elevator company was coming to adjust the closing pressure on the elevator doors. And in the transition between the regular lobby and the elevator lobby, we were measuring a 15-mile-an-hour wind in the pathway between those two lobbies. So this was an extreme case, but it is more typical than we think. So how do we do building envelope retrocommissioning? We perform all different types of tests. Oops, sorry. We perform all different types of tests, limited blower door tests. The bottom right-hand corner is an air fenestration leakage test. The one on the left is 2. The one on the upper left is a opaque wall air leakage test where we build a pressurized chamber on the outside, fill it with smoke, stand on the inside and see if smoke is actually penetrating through that bluish, purplish waterproofing you see on the outside, which is technically the air barrier, although it also functions as the water barrier. So when that leaks air, chances are it will also leak water as well. These are all during construction or after construction occupied buildings. These are tests that can be done. Here's something that's a little different and a little more cutting edge. Those silver squares you see up on the window are all called heat flux sensors. And they are actually measuring the transfer of heat through this window, which was a full-scale mock-up that we did for a project, and we asked the owner if we could keep the window and wall afterwards to perform thermal testing on it, because this is a very typical building wall right now. It's a 6-inch steel stud with gypsum exterior sheathing, an air barrier, insulation, brick cladding, UPVC window. This is what you see going up today on 90% of the affordable housing and mixed use buildings out there. This is very typical. The brick could be substituted for a more exotic material, but this is your typical steel stud wall construction that you see going up all over the city right now. And our idea here was to start looking at thermal bridges, which you're looking at the biggest thermal bridge you have in your wall, which is a window. We don't call it a thermal bridge because no one wants to hear windows are bad, and I'm not saying they are. But if you're measuring how much energy is lost through a wall, obviously the big hole in it is the worst performing part of the wall. That doesn't mean we shouldn't build with windows. We need windows for ventilation, light, comfort, but we have to understand that there's a trade-off between more fenestration and less performance. And what we're trying to do here is zero in more on how much of a trade-off we have to make for windows. And what I don't have a picture of here is we're starting to put these sensors that measure that heat conduction behind lintels, on the interior drywall, behind the stud area, behind the clear wall area, behind the sills. Everything that we're starting to talk about in the building code that you need to report your thermal bridges, right now it's reporting. You give it 1 or 2 more cycles of code development, and you will have to calculate that thermal bridge and factor it into your overall design. Right now, we don't really have actual performance, and that's what we're trying to do, is do a lot of R&D work on what does a steel stud do for your overall efficiency of your wall. We have guidelines based on modeling. We'd like to physically measure it and see exactly what it's doing. And that's been a project we've been working on for a few years now. So this is more examples of that in existing buildings, and these were all existing. The bottom right-hand corner is a commercial building by Rockefeller Center. It's a 65-story 1950s high-rise with stone cladding and vertical strips of windows. The one above that is an apartment. No, that's a university building. It's a dorm at a university. And this is just showing you some of the heat flux measurements we do to determine the actual U value, not U factor, but U value of those fenestration products. And then the R value of the opaque walls, which in this case is the stone. So we're measuring the conduction. And if we combine the conduction measurement with the air leakage, we're hitting two of the three big sources of energy loss through your envelope. So convection and radiation are the other two that we really don't get to do much about. Radiation is very hard to control. It's the sun, which we're talking about controlling solar radiation. You can do shading, interior shading, exterior shading. People like the look of architectural sun shading devices on low-rise buildings. They're not really practical on high-rise buildings, but there are other things we can do. Tinted glass, which most people don't want to see tinted glass on their projects, but we are probably getting to the point in the next 4 or 5 years where you won't have a choice, because you're just going to need to control the solar radiation or the solar heat gain, the SHGC that you see a lot. We need to control it, especially in high rises in New York City that are mostly glass. Convection isn't significant. It's the cooling that happens when streams of air hit the vertical surfaces of the building. So it's mostly detrimental on glass and aluminum buildings. So all glass towers, convection, the wind hits the wall, it has a cooling effect because aluminum and glass have what we call very high diffusivity rates. So they transfer heat quickly. And if you blow on soup in a spoon, you can cool it down quickly. But if you blow on rice, it doesn't cool down as quick. Think of building walls like that. Brick, stone, concrete, while they have crappy U and R values, they don't transmit quickly. So the gust of wind isn't going to affect those types of walls as quickly as they will an aluminum and glass wall. So there's no easy button for energy retrofit work when it comes to facades. And that's good news and bad news. The good news is for everyone who's on this call, it probably means lots of business opportunities for you guys in the future. Educate yourself now. There's a lot out there. It doesn't have to be high-rise specific. I love a gentleman named Joe Stiburek, and it's spelled Stiburek. And if he has Coffee with Joe, I think is his podcast, but he's got a ton of YouTube videos online. Again, it's Joe, Lstiburek. Look him up. That is a true building science guy right there. And the principles he teaches, even though they're mainly concerning low-rise wood frame construction, they're all applicable to everything we do here as well. He's one of the pioneers of building science. Um, I've learned I've learned more from him than I could ever repay him for, and I really do suggest people start looking him up. John Straub is another one. There are a lot of building science people out there that are giving true building science information away for free. And then it's the team. If you guys are going to be serious about helping people who own and occupy buildings tackle this local law 97 problem, you need to start assembling a team. Make those relationships now. If you're an architect, start talking to mechanical engineers you work with. If you're a mechanical engineer, start talking to building envelope consultants you're on jobs with, and start developing that team, because this work is coming, and when it hits, it will be a flood. I'm disappointed, as a lot of other people are, that the current administration has been kicking the can down the road on Local Law 97. We still don't know what the final outcome is going to be on dates and limits and all kinds of other things. They seem to be in flux right now, but it will happen. Whether it's next year, 3 years from now, there's no way around it. If we don't reduce carbon emissions, we all know it's going to happen. We've been hearing about it for decades now. So buildings are where we can do our part, and we will. You guys all will. So this is a very simple starting point. Um, you're sitting in a room right now. That room is probably 72 degrees Fahrenheit. Now, this was winter conditions, and outside was supposed to be 32 degrees. Today's not the right day because it's probably the same temperature inside and out. But imagine it's the middle of January and it's freezing outside. Heat's going to flow from hot to cold, just like you learned in high school. And it wants to flow through that wall in that direction. It wants to go from hot to cold, just like that arrow is showing. Now, this is a 80s building or a 70s building, CMU backup wall, brick, minimally insulated cavity, maybe, some flashings, interior drywall or plaster, and then a fin tube right below where it says 150 degrees. So that's behind a radiator cover or a wall or a convector cover. The air in the room is the same that you're sitting in right now, 72 degrees. But the air that's near that radiator, and it's called a radiator because it radiates heat 360 degrees, some of that heat is radiating into the building, into the room, and some of it's radiating straight out of that wall. And every one of those materials, the block, the brick, have very bad R values or very high U values, meaning they transmit heat readily. That superheated air that's behind there is flowing through that localized area, that 4x4 area behind the radiator, 5 times faster than it is in the rest of the room. That's 72 degrees. Source heat is much higher. Transmission is going to be much higher. It. Remember what I said about going from hot to cold. It always wants to move in that direction, and it will move faster the larger the delta T, or the difference in temperature, is. So from 72 to 32 is a 40-degree difference. It will flow at 10 miles an hour. 150, and it's not linear. So 150 degrees to 32 degrees, it's going to flow at 60 miles per hour through that wall. So it's going to flow much faster and much more, creating cold spots and, again, feeding itself, because that wall is inefficient. It's going to be a very large source of heat loss that you could see and even feel. If you walk on the outside of a setback on a building and put your hands on that brick, you will know exactly where the radiators are and where they aren't. You don't need a thermal camera to do it. I'm telling you, in November, you can feel it through the brick. You'll feel the heat coming through. So one of the things that we tell people to look at right away is these areas, especially on buildings that were built pre-1980 or 85 that didn't start using PTACs and more modern equipment. This is a traditional building, whether it's a fin tube like this or a 5-tube radiator. You have a water-based heating system that's superheating that air. Let's insulate right behind that system. If you stop that 4 foot by 4 foot square of very high heat loss, you'll probably reduce your heat loss through that wall 50%. I won't get into exactly why that's happening, but you will. And this is something that can be handled without displacing tenants or occupants. This is something that, although the materials are costly because you're going to use very high efficiency vacuum insulated panels or aerogels, because you need very, very high insulating values in a very, very small gap between the radiator and wall. So it's an expensive material, but used sparsely on your wall. So you're going to gain the maximum benefit from looking at an area like this and telling the owner of the building, your client, listen, we can do a lot by just attacking one area at a time. And that's where the smaller models, I talked before about the global model, using that Energy Plus or eQuest model as the global model. Here's where a mechanical engineer can do an analysis of the heat loss here. We can measure it and tell them, this is what we're losing. This is how bad the walls are performing. Then we tweak the insulation that we put behind there and then calculate the ROI. And that will really make a huge difference for people on their energy loss through the walls. So I'm going to just say thank you to everyone. This is a QR code. I have a couple of handouts that normally when it's a live event, I will give people, but if you guys can scan that QR code, it'll take you to a Dropbox link that has a building envelope guide and a short article that I wrote about time and the towel of sweaters that you might find interesting. So I think I went over a couple of minutes, Southpaw, but I apologize.
You're forgiven. You're really good. Really enjoyed it. Thank you so much. We have a few questions, and I'll go straight into them. Sarah's question is: Has the accuracy of our measuring tools on the has the accuracy of our measuring tools on site improved over the years, as well as increase in data points?
So the accuracy, so some have, obviously. We're getting more, and mostly on the mechanical side. So electrical and mechanical, we do see people starting to monitor watts, temperatures in more spaces, because the cost of that equipment to do that, a hobo sensor now is $150 and it logs for a month. So you can get in there or it's connected to the internet. So yes, that's increased the accuracy, because now we're actually able to take the measurements and collect the data, which 10 years ago was $1 million investment. Today it's 2,000. So it has. The data points, we're all about data points. That's what we do. We log data. We don't take a picture anymore of a reading and say that's the number. We're looking for more data points, so many that we had to actually find software that could deal with the 40 million data points that we're dealing with. But yes, it has been, thanks to technology and technology coming down in price.
Sarah has another question, and then I'll circle back to Arthur. Are ultrasonic air leakage sensors in broad use?
Not yet, but you know, the sensor itself isn't as important. We're not trying to measure air going into a jet engine or into your car. But if you own a car and it still uses a gas engine, that's one of the industries we have to thank for cheap sensors, because you have what's called a mass airflow sensor in your car under your hood that in horrendous conditions can measure so accurately flow of air. And when we do an air measurement or an air leakage measurement, we're measuring the flow of air, just like you're measuring in a duct. So while ultrasonic stuff hasn't been really taking off here, other forms of it are. And we use very, very basic sensors like pitot tubes or averaging pitot tubes, and they're more than accurate enough to do what we're looking to do.
Thank you. Arthur's question is: What is the future of glass and steel buildings under Local Law 97?
So the future is we need to get smarter about doing it. The technology has been there for a long time to allow us to make aluminum, which is an awesome building material when it comes to everything but thermal properties. I mean, it's light, it's strong, it's aesthetically pleasing, it's easy to fabricate, and it sucks thermally. That's the problem with it. But for decades now, we've known how to improve it, and we just haven't done it because of the cost. So it's time to start demanding more from the manufacturers and telling them, listen, I want substantial thermal separation between the outside and the inside. I don't want the code minimum because what they're telling you meets the code. It met the code once when they modeled it. And then every other window that you bought that wasn't the exact size and configuration of the test report they sent you was different. And bigger with larger pieces of high performance glass perform better, and smaller, maybe with more intermediate horizontal and vertical mullions, perform much, much worse. And that's one of the metrics that I said we need to work on, because falling in love with the model means more than just the building energy model. You're going to get to the point that if you want to build a glass and steel or a glass and aluminum building, you're going to need to demand that they model every inch of that job, even a punched opening window job. You will have to start getting thermal simulations of every configuration on the job. You can't just accept the report after this. As far as glass goes, there's some cutting edge stuff happening, the aerogels and vacuum glazing that I think are a game changer. Vacuum insulating glass is definitely going to be a game changer for us, and will allow us to still build the way we want as long as the aluminum guys get their act together.
Thank you. Could you go one slide back? I think people are trying to get your queue up, but yeah.
Sure.
So we don't have any additional questions, but I'm gonna have you leave this slide just for those who didn't manage to get the QR code.
Sure.
Um, any other last parting notes, Elliot, that you would like to share for any kind of basic tools that you think we should have in our, in our offices, just to go on site with that, just if we're starting the journey of like measuring and verification?
So start with the basics. Find that when you're talking to a client, explain to them that this is a journey and it's a long journey, that there's no quick fixes, there's no playbooks for this. I know you can go to the BEX website and download some playbooks. They're guidance, they're not really a plan, they're just telling you the big picture stuff. Start with, as I said, the basic information on a building. What's the size and shape of the building? What type of roof does it have? And really dig into it. How many different wall types are there on the building? How many windows are on the building, right? What type of windows are they? This is stuff we all learned as junior architects how to do. Go out and do a site condition, survey a building. It's not tough. It doesn't take knowledge of expensive software. It's just creating an actual record of the building. And that's where you start. Then get to the owner and say, I need the statistics of the building, especially when it has to do with occupancy, but also ask questions like, when do you start your heating system? Is it October? Is it November? Is it never off? Is it never on? When do you start cooling? They have dates usually that they do that, or they say when it hits this, they're going to turn on their system. That's important to know. How long do they run the systems for? How many months of the year are they running both systems? So, especially in New York City with high-rise buildings, you'd be surprised how many owners are going to tell you, we never shut off the air conditioning because the bottom of the building is always hot, cold, the top of the building is always hot. So we're running both systems all year round. That is so much more common than people think. And for retro commissioning, this is where you start. You start by becoming familiar with the building. And owners have to understand, I don't know if we have any on, but they have to understand that program manager, which I believe the most appropriate person is the architect. You have to pick that person very, very carefully because that person needs to stay your architect like we used to do in the old days for 20 years. This is different business than we become used to. Retrocommissioning and compliance with these carbon reduction laws are going to require a long-term relationship between a building and their architect, because there's no one else they can trust. Salespeople are just going to sell them on a dream. If you just change these windows, put in this insulating glass, it's going to fix all your problems. I had someone call me this morning asking me about changing out gaskets that they thought was going to be a major step forward in carbon reduction. I said, I'd love to see it, but I don't think so. You need to develop that relationship with these owners. It's a different approach to business for us, but it is more traditional, because in the old days, a developer worked with an architect. They stayed with that architect. They trusted that architect. If you guys can get this going, you will gain that relationship with your clients that will last decades now, not till the end of the job. And then they shop for the next professional like they're buying floor tile. That's not what we want. We want to be able to gain their trust, which they should, and we want to have these long-term relationships with clients. And they need that, because believe me, you're like doctors when it comes to this. You want to go to your family doctor and say, I have a pain in my knee. Can you recommend a specialist? And can you look at the results that the specialist tells me and tell me whether or not this is real? I need to go for a second opinion. You have to think of it along those lines. You guys really are becoming like doctors for these people to help them fix their buildings' health issues.
Thank you. And on that note, there'll be some kind of fixing on your part, Elliot. The QR code, people having slight issues with it's not going to the Dropbox, but what we'll do is we'll send out an email to everyone so they have access to it, so we can do that separately. But I want to thank you so much for all this knowledge and sharing, obviously, other building scientists that people can, reach out and gain more knowledge, and also just kind of holistically bringing back to relationships and looking at it in a much more simpler format. So thank you everyone for coming, and thank you again, Elliot.
Thank you, Paul, and thank you everyone at the AIA for putting this together.